Hi, this is Dr. Goldstein, and today I'm talking about limits of exponential and logarithmic functions. So let's start with exponential functions, and in order to do this, I want to start by talking about powers of 2. So we know that 2 to the 1 is 2, and 2 squared is 4, and 2 cubed is 8, and 2 to the 4th is 16, and 2 to the 5th is 32. And if we keep on taking bigger and bigger powers of 2, we know that we'll get larger and larger numbers. So 2 to the 10 is 1,048, and 2 to the 20 is actually 1,048,576. And so you can see that the powers of 2 get big real quick. So what we can see with this is that if we take the limit as x goes to infinity of 2 to the x, so again, what this means is that we're letting the exponent of 2 get very, very big. We are going to get very, very big numbers. So this limit goes to infinity. Now, let's see what happens if we go the other direction. So if we start taking negative powers of 2, 2 to the minus 1 is the same as 1/2, which is 0.5. 2 to the minus 2, that's 1 over 2 squared, 1 over 4, which is 0.25. 2 to the minus 3 is 1/8, or 0.125. 2 to the minus 4 is 1 over 16, which is 0.0625. And 2 to the minus 5 is 1 over 32, which is 0.03125. So you can see as we take bigger and bigger negative powers of 2, we're getting smaller and smaller decimals. Just to convince you a little bit more, if we compute 2 to the minus 10, that's approximately 0.000977. And 2 to the minus 20 is absolutely teeny. It's 9.5 times 10 to the minus 7. So that's 0.000000. That's 6 zeros, 95. So we get really, really small numbers. So what we see from this is if we take the limit as x goes to minus infinity of 2 to the x, so I take negative powers that get bigger and bigger, I get numbers that are closer and closer to 0. So the limit as x goes to minus infinity of 2 to the x is 0. And now generally in mathematics classes, we talk about exponential functions with e. So remember that e is approximately 2.718. It behaves similarly, and in fact, any number greater than 1 is going to have these same limits. So what we have is that the limit as x goes to infinity of e to the x is equal to infinity, and the limit as x goes to minus infinity of e to the x is equal to 0. And just as a side note here, this limit is actually 0 plus, since we know that e to the x, or any number to a power, is going to be greater than 0 for all x. So that's just a side note. This will be important later. For the moment, when we describe limits and it goes to 0, we don't care whether it's plus or minus, just the function gets closer and closer to 0. Okay, so that's limits of exponential functions. Let's talk about limits of logarithms. So the first thing that we want to remember is that when we're dealing with logarithms, they have a restricted domain. In particular, the domain of the natural logarithm, or any logarithm, is just positive values. So you cannot stick anything into a logarithm that is either 0 or negative. So the domain, x must be positive. So now let's think about a couple of different limits. If we take the limit as x goes to infinity of the natural log of x, let's think about what this means for a moment. So the natural log of x is equal to some value y. This is the same as saying that e to the y is equal to x. So we think to ourselves, for a large x, you need a large y. You need a large exponent of e if you're going to get a big x. So I need a large power of e. So what that tells me is that the limit as x goes to infinity of the natural log of x, this is equal to infinity. Because if I want e to the something to be bigger and bigger and bigger and bigger and bigger, that power, the power is this x, sorry, the power is this y that we're going to, that also needs to get bigger and bigger and bigger. So we have this limit. Okay, so the second one here, let's look at the limit as x goes to minus infinity of the natural log of x. And now remember our domain issue. We cannot plug negative numbers into the natural log. So the domain is x greater than 0. So this limit just does not exist. We can't take this limit because I can't plug in any negative numbers to a natural logarithm or any logarithm. The same thing with 3, with our limit as x goes to 0 from the left. This also does not exist because x approaching 0 minus, this is when x is less than 0. So the natural log of x is not defined. So we actually can't take these limits. They just don't exist. On the other hand, we can take the limit as x goes to 0 from the right. So in this limit, x is positive and it's small. So again, let's think about if the natural log of x is equal to some y, and let's flip that around. So we have e to the y is equal to x, and we think what y gives us x close to 0. So i.e., e to what power is approximately 0. And that's what we're looking for. That y is what we're looking for this limit. Well, what we saw on the last slide is that we need a large negative power. And so this limit, as x goes to 0 from the right of the natural logarithm, this is going to be negative infinity. So we get 2 more limits with logarithms, but we can't just do infinity and minus infinity. We can do infinity, or we can do 0 from the right, because again, that is the edge of our domain. So we're looking at both sides of the domain of our function. Okay, let's take a look at this visually so that this can make a little bit more sense. So what we saw on the first slide, so this green curve is y equals e to the x, and I've drawn in the point 0, 1 for your reference. What we saw on the first slide is that the limit as x goes to infinity of e to the x is equal to infinity. And that's what we see over on the right here. As x gets bigger and bigger, the values of our function get bigger and bigger and bigger as well. And we also saw that the limit as x goes to minus infinity of e to the x is equal to 0. And that's what we see on the left-hand side here. As the values of x get bigger and bigger and bigger in the negative direction, the values of our function get closer and closer and closer to 0. So another way of saying that is that e to the x has a horizontal asymptote of y equals 0 just to the left. Okay, for logarithms, this purple line is y equals the natural log of x. And remember, e to the x and natural log of x are inverse functions to each other. So the purple line is the green line flipped over the line y equals x, which is in red. So on the green curve, we have the point 0, 1, and on the purple curve, we have the point 1, 0, because I've switched the x and the y coordinates. So what we see in terms of the limits is over on the right, we have the limit as x goes to infinity of the natural log of x. This is equal to infinity. So it kind of doesn't look like it, but that's what happens. The values of the natural log of x get bigger and bigger and bigger. And then over here, again, at the other edge of the domain of this function, we see that the limit as x goes to 0 just from the right of the natural log of x is equal to minus infinity. So in other words, the natural log, or any logarithm, has a vertical asymptote at x equals 0, but just on the right. Again, because logarithms just aren't defined for negative values, so we cannot look at the other side of that function. So let's look at a little bit more limits with e. So the actual definition of e, people ask me about this, and they're like, what is e? Well, it's kind of like pi, but it comes from a different place. And the actual definition of e is that it's the limit as h goes to 0 of the quantity 1 plus h raised to the 1 over h power. And we'll see why later. And the short answer is that it has to do with derivatives. So because of derivatives. But for the moment, this is the definition of e. Now, a theorem that's related to this definition is when you take the limit as h goes to 0 of e to the h minus 1 divided by h, you just get 1, which is kind of surprising. So we could ask why this is true. So this is the limit of the form 0 over 0. But what we do is we think that when h is very, very close to 0, we look at the definition of e, and we say, okay, well, for h very close to 0, e is approximately 1 plus h to the 1 over h, and this is the definition of e. That's that definition up there. Now, if we take the h power of both sides, we have e to the h is approximately 1 plus h. And then if we subtract 1, we have e to the h minus 1 is approximately h. And then we divide by h. That's exactly this theorem. So for h close to 0, we see that the definition in 1 tells us the limit in theorem 2, that e to the h minus 1 divided by h gets very close to 1 whenever h gets close to 0. So let's see some examples of how to use this definition. In our first limit, we have the limit as x goes to 0 of 1 plus x raised to the power 3 over x. And if I think creatively with exponents, I can write this as the limit as x goes to 0 of 1 plus x to the 1 over x, all raised to the third power. And now I look at the inside of this and I recognize it as the definition of e. And so overall, when I take this limit, I just get e to the third power, which is a number. Remember, e is approximately 2.718, so this is less than 27. So this limit problem, it looks really awful, but if I think creatively and remember the definition of e, it's actually not so bad to solve. Now, the second problem here is a little bit harder, and once you've seen it a few times, you learn to recognize it. This is the limit as x goes to infinity of 1 plus 1 over x raised to the x power. Now, the thing that I notice here is that as x goes to infinity, 1 over x goes to 0. So if we substitute x equals 1 over h, then h is 1 over x, so h goes to 0. So if I substitute h for x, I'm taking the limit as h goes to 0 of 1 plus, remember, x is 1 over h, so h is 1 over x. This is the limit as h goes to 0 of 1 plus h raised to the 1 over h. And so again, we recognize that this is the definition of e. And so this limit, again, it looks really nasty. This limit is just equal to e. So this last bit is really just kind of fun things that you can do with some really complicated looking limits because of how we define e. And again, you'll see the motivation for that definition in some later videos.